So imagine you have one manat and you found a bank that gives you 100% of that one manat.
Well, 100% is very generous for a bank.
Yeah, quite generous.
Yeah.
So giving you 100% means that by the end of the year, your money will double. So one manat will become two manats
2 minutes.
by the end of the year.
Yeah.
But what if your bank gives you a smaller amount of interest and it's compounded more regularly?
You mean 50% compounded, say, every 6 months, twice a year? So in such a situation, you will have 1.50 manats in 6 months, and then in the second half of the year, your bank will add additional 50%, and this will make up a total of, I guess, 2.25 manats, right?
Yeah.
By the end of the year. So that's greater than the value I've just calculated, greater than 2.
But I have a question. What if your bank gives you a 25% of interest and it's compounded, let's say, quarterly?
Okay, yeah, so it's 25% quarterly. Yeah,
Right.
luckily I have a calculator with
Oh,
me.
great.
Of course.
So I have one manat. What does bank do? It divides that one manat by 4 and adds to the amount that you have.
Okay.
So one manat will become 1.25 manats.
Obviously.
Now bank, that's the amount you'll have by the end of the first quarter. Now bank divides it by 4 again and adds to the amount that you
previous
have.
value.
Yeah.
Okay.
So you'll have 1.56 manats by the end of the second quarter.
Okay.
Again,
So just repeating the same steps.
yeah, bank will divide this by 4 again and will add
And the
to
previous
the amount
Okay.
you
Right.
have. So you're gonna have 1.95 manats,
And fourth time?
and that's by the end of the third quarter.
Right.
And again, it divides by 4 and adds to the amount you have. So, nope. So you'll have 2.44 manats by the end of the fourth quarter, by the end of the year. Yeah. That's more than 2.25.
And even 2.
And even
yeah.
2.
Yeah.
Yeah, right. So now I have reasons to be quite optimistic that if we are lucky and we can find a bank that gives us a very tiny amount of interest and it's compounded so frequently, let's say every hour, every minute, or even better, every second.
Every second?
Yeah.
Oh, so
It
you
would
mean,
be quite beneficial, I think, no?
well, you mean, do you think that just one manat you have original deposit will turn into a million
So I
just
guess
by
so.
the end of the year by such calculations? Because it doesn't really sound very plausible. What do you
Plausibly
think?
identical.
Yeah, I also tend to think that there will not be a million,
Yeah, obviously.
but in science you have to be skeptical, right?
Yeah, we should be.
Let's check
Let's
it.
check.
Let's check it.
So this was a question that interested famous Swiss mathematician Jacob Bernoulli, who was trying to calculate the final amount one could get at different interest rates. And the scientist was particularly interested in a situation with infinitely small interest compounded infinitely many times a year.
Now, Nurlana will repeat the exact same steps as our bro Jacob did, and she will use Excel for that.
So Bernoulli used the following formula to find the final amount of interest. Final amount is equal to 1 plus 1 over n in the power of n. And now I'll demonstrate the process performed by Bernoulli, and I'll use Excel for that. I'm going to construct a table. So I'll begin with my preparing of 3 columns. So let's begin with the first one. Okay. It's ready. The second one. Nice. And the third one I'll prepare later. So let's write the formula here, but first of all I want to explain you that I'll use the final amount of interest, and that's why I'll write how often our interest is compounded. So first of all I want to write 6 months, then more regularly 4 months, even maybe 3 months, 2 months. More often, let's take 1 month, every month. So let's take, for example, every week, every day, every hour, every minute. What can we take? Something more? Let's take every second. So every second. And now I want to write the formula used by Bernoulli for this. So I'll write it here. Let's write down our formula. So it's 1 plus 1 over n. So n in the power of n. Perfect. And now I want to write the values. 6 months, it means that it's compounded twice a year. So I write here 2 instead of n. 4 months, it means 3 times a year, 4 times a year, 6 times a year, 12 times a year. Every week, as I know, there are 52 weeks in a year, so 365 days. Hours, so it's a little bit harder. It's 8,750. No, it's 60. So minute, it's this value, and second is the most extreme one, I guess. So okay. And now you can see that I have prepared everything we need in order to find our final amount of interest. So I'll just look what our formula gave us. Okay, nice. So wonderful. You can see that we have these amounts. It means that if our interest is compounded every second, we get the value that is 2.71, 82, and 82. But I want to mention the fact that, as you know, we took the firstly our currency of 1 manat, and if it's compounded, it can be in millions or in thousands. It can just stop in hundreds, because, as you know, 1 manat is composed of just 100 cents, and that's why it will stop at every day, because it's equal to 2.71. But if you want to see more exact values, you can see that it's equal to the number that we'll explain you a little bit later. Let's remain it a mystery.
Our friend Bernoulli noticed that the final amount he calculated was coming closer and closer to some particular value, but he could not actually calculate it with precision in financial context, and this was done later by Leonhard Euler.
And when it comes to his inventions, he has created a number of various inventions. For example, he gave the name of function f of x, he named this function, and also he named the sum of all units as a constant sigma. He as well popularized the value of pi, and also helped to the imaginary unit I to be widespread.
And one of the interesting formulas, he derived the formula e to the power of pi I equals -1, where he gathered all 3 constants together.
Yeah. And now we would like to provide some personal life background about this wonderful person. There happened a number of unfortunate events. First of all, in 1766, he lost his sight, but due to his mathematical abilities and his great memory to process things, he could continue his research. And also his son, Jonathan, played a crucial role in his life by transcribing his words in the paper. But another disaster happened in 1771, when there happened a huge fire and his house was burned to the ground. But due to the servant of Leonhard Euler, he could survive, because his servant carried him out from this house, and fortunately he did not lose his life.
Yeah, and again, when I was doing the research about the Euler, I found out, and I was shocked about this information personally. I found out that he worked in St. Petersburg, and he knew Russian fluently thanks to his father, and he was very surprising for me.
That's
Wow,
amazing.
that's amazing, yeah.
Yeah. So now we're going to talk about the mystery that Nurlana mentioned earlier. This is some number. So in his works, one of his works, Euler, came up with this number. So the number goes like this. It's 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over. Now you expect that I write here 2 again, but no, it's 1 again, 1 over 4 plus 1 over 1 plus 1 over 1 plus 1 over, now guess what the number is, 6 plus 1 over, and so on. And he somehow could calculate the value of this big fraction, and he found that it equals to approximately 2.718281828, and so on. And then he came up with the notation of this mysterious number, and he noted this as E. Now, and of course we have to mention that this letter E is not because of his first letter of his surname, Euler. It's just a coincidence, just the letter A was used already and he picked the next vowel letter E. That's it.
Well, actually, the number that Mr. Elnur has just derived is very similar to the one that I found as a final amount of interest in my previous part. So I'll write down the formula used by Bernoulli. It's equal to 1 plus 1 over n in the power of n.
That's just the same formula used to
Yeah, exactly, the same
Oh,
one.
yeah.
And if I write that the limit of n as it approaches infinity, it's equal to e, the natural number e.
Okay. Well, an amazing formula indeed. So.
You're really great.
Yeah.
So I'm gonna show one more way of deriving the number that we are talking about, and for this we will take the sum of reciprocal factorials. So the formula is here. The thing that I'm gonna do is written mathematically like this. This means that I will take 1 over 0 factorial plus this sign, sigma sign means plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, plus 1 over 5 factorial, and plus until so on until infinity. Okay, so and I will use, as you see, Excel for that, because Excel is a great software for doing this kind of stuff. So I will take 0 in this column. I will write the numbers so that I can keep track of the things that I'm going to do. So it's 0. 0 means that I will take just 1 over 0 factorial. Right? We know that 0 factorial is 1, so 1 over 1 should give us 1. Okay, now let's take the sums until 1. So 1 over 0 factorial plus 1 over 1 factorial. So we know that 1 over 1 factorial is 1, 1 over 0 factorial is 1, so that's going to be 2. That should be 2, and that's 2. So now let's take this sum until 2. So that will give us 1 over 0 factorial plus 1 over 1 over 1 factorial plus 1 over 2, I guess. Yeah, 1 over 2 factorial, and that's going to be 2.5. And I want to repeat it until infinity or until the huge number as much as I can, as much as my computer can. So let's now take 3, but I don't want to write that down. I want to write the formula. So what Excel provides, it provides the opportunity to do this kind of stuff with the formulas. So I'm going to write, I want to sum 1 over factorials, right, of the numbers from here till here. All right. Oops, what is it? No. Okay, it should be all right. I missed the bracket sign, and I will put the dollar sign here. Don't pay attention to this. Yeah, it's 2.666. All right. So 4, I want to add the factorials until 4 factorial. So that's going to be, all right. So what it does, it just takes 1 over factorials from 0 to 4. Now, I just want to drag this down until, let's say, 23, and also here. Okay, as you can see, until somehow like 15th factorial, it just repeats itself I guess my computer, it doesn't have enough resources to calculate. And let's take this and expand till a very... Oh, okay. Okay, here my computer crashes, I guess. It doesn't have enough resources to compute this. Oh, okay. So after 170th factorial, like after it added 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorials, and so on, 1 over 70 factorial. So it crashes, like doesn't have enough resources. But fairly, I can say that after, yeah, it's just the same thing after 15th factorial. And if you look up on Google the exact value of the number that we are talking about, you can say that the digits are the same, like here. So after 15th factorial, it's already a great approximation. So this is it. This is the other way you can find the natural number.
Thank you, Mr. Elnur, for your explanations. Natural number E occurs in many different equations and has different applications in statistics and probability. Now Ali will clarify this part.
Number E has a wide range of applications in the area of statistics. And when I said that, I'm specifically referring to the normal distribution function. And I will sketch its graph for you. First of all, I will draw an xy plane. This will be my y-axis. And perpendicular to it will be my x-axis. And its continuation here. This would be my origin, and as I've said before, this is my x-axis. So distribution function shows distribution of features in our sample. And the first thing we have to do when sketching it is to find our mean, because it always has the greatest value of y. And let's say mean is here. And as our x values go further from our mean, the frequency will decrease in both directions. So it will look like this in the positive side of x values, and it will be symmetrical with respect to y-axis here, like this.
It looks like bell-shaped curve, right?
Yeah, it's very similar to bell-shaped curve, and you may have actually wondered what's the function that defines this curve. And I will write it for you. It's function of distribution phi, which depends on x, sigma and mu, and it's equal to 1 divided by sigma square root of 2 pi multiplied by e and raised to the power of x minus mu squared, and this is all term divided by 2 sigma squared.
What a scary formula.
Yeah, actually I had the same impression when I first saw it.
And I'm quite curious to know what else this letter mu stand for.
Yeah, actually I've already mentioned it before. It's our mean. And I guess you know what the mean is for this curve.
0?
Yeah, it's 0, because let's say just y value is the greatest here, so this would be my mean. And,
also, one more question. I know definitely what this letter is. It's pi,
of course,
that's for sure. But what about this?
Oh yeah, it's Greek letter sigma, and it means deviation. Deviation. And for any sample, deviation represents a diversity of features. Say, if our sample is uniform, say our features are all very close to mean, deviation will be smaller. But if the range between the features is very large, our deviation will be much greater. But again, the greatest use of this formula is in its cumulative form, which I will also write here. It's phi, which depends on the same values, say x, sigma, and mu. And I'll just rewrite this left-hand side term, 1 over sigma square root of 2 pi. But now, instead of just writing in the same way, I will put an integral of the e raised to the power of x minus mu squared to sigma squared. And if I'm integrating, I have to put bounds, lower and upper bound. And of course, if I have an integral, I'll put a differential.
One more scary formula.
Well, yeah, I would agree actually, but again, it's very useful. It's super useful in finding different features. For example, and just a minute, I'll put, say, A here, and say this would be our B, which are again just some x values which I have randomly chosen. And if I raise perpendicular lines to my graph, this function would explain what fraction of the whole area is located in this range. So just refer to this area between these 2 points. And this is very useful in real life. For example, if you have already taken your SAT test, and if you have received your scores, okay, and you may have noticed such thing as a percentile. Yeah, percentile. And to calculate the percentile, they use this formula. For example, if you have, a score in 95th percentile, this means that the 95% of all test takers scored lower than you did. And for this function, it just means that the whole area of the curve that's located to the left from this point comprises 95% of the whole area. And say, I will color this part. Yeah.
And that would mean that 5% of the population will be here.
Yeah,
right?
exactly. And this would be, let's say, those people who scored higher than you did. Yeah, and in fact, this function is super useful not only in mathematics and statistics, but also in natural science, in biology, chemistry.
Well, it's really amazing, but sorry for interrupting you, but you have told about us statistics, but what about probability?
Oh, yeah. Actually, I will be very surprised to just realize that this number is very useful in some casual situations. For example, say we are playing in a lottery, and our chance to win is 50%. I'll write it here, 50%, right? And if I write it as a fraction, it's 1/2. Then, to find the chance of losing, I will have to subtract it from 1, which again gives me 50%, right? And say we play the game twice. Then, if we want to find the probability to fail twice in a row, we'll have to square this term. And let's actually calculate it. 1 minus 1 divided by 2 and the whole term squared, which gives me 25%.
So it's the probability of failing twice in a row.
Yeah, exactly. And say if our chances are smaller, if we have, say, 20, okay, 20% chance to lose, to win, then it's equivalent to 1/5. And if we want to find a chance to lose, again, we'll use the same steps. I will subtract it from 1, like this.
And that's going to be in the 5th power.
Yeah, exactly,
right?
because we're trying to find a probability that we'll lose 5 times in a row with such a chance. And again, I'll use my calculator. It's 1 minus 1/5 raised to the 5th power. And it's approximately 33%, right?
But what if our chance of winning is very tiny?
Well, I guess it would be more realistic. And let's take 1%. Okay. If we have 1% win, which is equivalent to 1/100, the chance to lose will be
identical
here.
steps.
Yeah, just 1 minus 1/100.
And I suppose we write it in hundreds.
Yeah, in the hundreds power, right. And again, if you calculate it here, it's 1 minus 1/100 raised to the power of 100, and it's approximately 36.6%.
It looks like the numbers, the values tend to something.
Yeah, exactly, because the difference here between 25 and 33 is much smaller, much bigger than the difference here.
Yeah.
And in fact, if I write it in this way, like 1 minus 1/n, and I raise it to the power of n, again, I was using this formula the whole way here. But say we play the game infinitely many times, and our chances are very, very small. So then the n will approach infinity. And in fact, this has a constant value. It's 1/e. And if I try to calculate it, it will be 1 divided by 1/e, which is 36.79 approximately. 36.79.
Quite close.
Yeah, when we're doing this part, we were already very close to its limit. Intimating that the natural number appears in just some usual situation. And in the next part, we will talk about different mathematical properties of this number, as well as about its applications in logistics and other, fields of mathematics.